Okay, this video will cover question 6, which is a question on moment. How do you know that it is about moment? Well, there are some hints for you. If you see things like turning effect, if you see things like pivot, it is actually hinting to you that please talk about moment. Okay, before I talk about the diagram, let's answer part A. Okay, so for your part A, you are asked to state the two conditions for equilibrium. So this is content knowledge. So this is part A. Okay, for your part B, basically what you need to be aware of is that this is the pivot. Okay, once you identify the pivot, you need to identify how many forces are there. So obviously there is a 6 Newton weight over here, followed by a spring balance which will pull the object up. So that's how I know that it is upward over here. Then of course at the pivot, there will be a normal contact force that is going upward. For example, if this is the pivot, it will be a pin that basically supports the rest of the ruler, right? This pin will exert a force upward. So whenever you have a pivot, chances are there will be normal contact force. And of course, since this ruler has mass, it will also have the weight. So in total, you will have 4 forces, right? Let me, how come cannot zoom? Okay, you will have a total of 4 forces, and each of these forces should give you a turning effect, which is the moment. But you can see that for normal contact force here, and for the weight over here, it is directly at the pivot, meaning that the perpendicular distance will be 0. So hence, for the normal contact force and the weight, there will be no moment, right? This one will produce no moment. But for the rest of the 2 forces, how come my spelling suddenly gone? But for the other forces, the T and the 6, there will be a moment. So if you do not know how to determine the moment, please come and see me. So for the T, there will be a moment this way. So we call T our clockwise number 1. And then for the 6 Newton, it will produce a moment this way. So we can see that it is going anti-clockwise 1. So basically in this system, there are only a clockwise moment and 1 anti-clockwise moment. And because the question says that the ruler is at equilibrium, that means it is balanced, we can then say that, if they are balanced, then the clockwise moment must be bigger than the must be equal to the anti-clockwise moment, right? Then after that, you just expand it to force times distance, you'll be able to find the spring balance reading. So remember 2SF. And then for part C, you are actually asked to find the upward force exerted by the pivot on the ruler, right? So this is your normal contact force, which is the N we have. So because this is an equilibrium system, your net force will be 0. So meaning that all my upward forces, my blue forces, my upward forces, should be balanced by the downward force, the pink forces. Right, so you don't even need to take moment again. You can just equate it this way. Okay, F net equals to 0. All my upward forces must be cancelled out by my downward forces. So that's how you can get N. Remember 2SF. Okay, question 7. This one, please refer to your textbook. 7B is similar. Okay, for 7B, lower and upper fixed point, it is by definition. So refer to your textbook. In this case, no need to change it to 2SF. You can leave it like that. Okay, for part C, if you have problem doing this, it means that you need revision. So this is actually from your homework worksheet. You're actually asked to deal with a thermocouple thermometer. So a thermocouple thermometer basically looks something like that. There will be a voltmeter. This is where you read your reading. Okay, then after that, there will be 2 wires that comes out. this wire will be the thing that you insert into the sample that you want to measure your temperature. So what it does is that for thermocouple, you need to put the cold junction into a reference temperature. Okay, reference temperature. So this reference temperature, most of the time it is going to be 0 degrees C. So this one is like your reference. Then after that, the hot junction you will be placed into something that you want to measure. And because of the temperature difference here, let's say this temperature is T, the temperature difference here will be T minus 0. Now you know why the reference is 0, because it's easy, right? You can put this in liquid nitrogen, right? But then your equation will become T minus 330. You are asking for it, right? So most of the time we will put the cold junction in 0 degrees C. So once you put things into different temperature, there is this effect called thermoelectric effect that will cause a current to run, and that is how you get the reading over here. Okay, so once you understand this, then it is quite straightforward. So here you see that they give you a reading 4 millivolt. Okay, then I write down here, this is my cold, this maybe I don't put cold here, I put hot first, easier. Hot and cold, and then my difference in temperature, right? So when my cold junction is in melting ice, so cold junction in melting ice means that it is 0 degrees C. Then my hot junction in boiling water, so this is 100 degrees C. So now I know that a difference of 100 will give me a voltage of 4 millivolt. Then it says I remove my hot junction from the hot boiling water and put it into something unknown. So meaning that now I put it into something that I do not know, and I register 2.75 millivolt, and my cold junction is still in ice, right? So if now I call this question mark T, then my temperature difference will be T minus 0, right? So it is quite straightforward. So I can use directly proportional. So my V is directly proportional to the change in temperature, right? This is content knowledge. You should know that thermocouple behave like this. Okay, you should know. So if it is directly proportional, then the math will become like this, right? If I call this case 1, so my case 1, I will have a voltage of 4 millivolt equals to K times 100. So this will give me a constant of 0.04. Now I look at case number 2. What is my case number 2? This. So in my case number 2, it follows the same expression, but now I know my K. So my expression becomes this. And my voltage now is 2.75, 0.04 delta T. My delta T is actually T minus 0, right? Here, T minus 0, the red one. So once I know that, I can actually solve for T and make sure to SF. Okay, so that's how you solve that.